Okay, so other than kind of rounding stuff to the right number, we also need to think about what we put after our answer in terms of, we put significant figures, but we need to think about, you know, what unit. Okay, is it in meters? Is it in seconds? Is it in kind of centipoises or some other weird unit? Okay, we need to get the right one, and this can actually help you actually do the maths. Okay, because if you know what unit your answer should be in, okay, you can use that to check whether you've rearranged your equations correctly. Okay, and this is a really useful kind of like tip. So kind of the SI or the standard standard international, which is kind of the French word for international standard, kind of units are for things like length, time, and mass being the amount of stuff, not its weight, are in things like meters, so as opposed to using feet or chains or cubits or some other weird thing. Meters. Time is always in seconds, okay, which is a little bit odd for geologists, so quite a lot of the time that you'll deal with will be in multiples of years, okay, and there is actually a difference between doing time in years and time in seconds, because seconds don't change. A second is a second, whereas if you go back in geological time, the length of a year is different. So, yeah, it's weird, but it's true. And that has small impacts on how we do geochronology and dating. Because if we use radioactive decay to date things, we use seconds, that's our standard. But if you use fossils, things like that, then your standard unit is in fact the year, which does kind of mess things up when you get to be really good at measuring stuff. Mass in kilograms, which is the odd of one of the units. So these are all of the 7 international standard units. So kilograms is the only one that is 1,000 of something. So all of the others are 1 meter, and then if you get 1,000 of those, you have kilometer. Whereas the kilogram is kind of the odd one out because its standard is 1,000 of grams, which is not the base unit. And there is a weird reason for that, apparently, which I can't quite recall. Something French. But anyway, so you don't need to know what all of these are. Meters, kilograms, seconds are the key ones. K, Kelvin for temperature. So you might see quite a lot of the time temperature referred to in Celsius, particularly in geology, but Kelvin is the correct one. Good Scottish unit. Bizarrely, candela for light, that still exists as a unit, the power of a candle. Right, so I'll just whiz through all this kind of stuff. There we go, it's control click on the computer. So the top terms, well, first of all, Vs is basically the settling velocity, how fast something falls vertically through your fluid. Okay. 2 and 9 are just numbers. Okay. So in this case, okay. So in the examples before I was giving with this kind of cheeky rounding example, okay. That's if those things were measurements. Okay. In this case, these things are numbers, as in they are constants in the equation. So you wouldn't round your answer to one significant figure because those numbers are one significant figure numbers. Okay? You can treat, when you're given a number in equation as opposed to a measurement, then that doesn't kind of impact how many significant figures you give stuff to. So the things that we have on here, we've got, this is rho, this curly p, so that's density. The density of your particle minus the density of your fluid. Okay, so this is basically the difference in density between your particle and your fluid. So if you've got something heavy in a light fluid, okay, or something dense in a not dense fluid, it will, because this number is on the top of this division symbol here, it means your velocity will be higher. Okay, so this is if you drop a big iron ball through air, it will fall faster than if you drop a ping pong ball in water. Okay. In fact, the ping pong ball in water will actually have a negative settling velocity because it will be rising up through the water because it's less dense than it. Okay. This term mu down here, so this is the Greek letter mu, Greek m, and that, bizarrely, mu stands for viscosity. So this is how gloopy the liquid is. Doesn't matter what symbol you use, but when you've got an equation like this in, say, an exam, and if you were asked, I mean, you won't be asked to do this for the maths exam, but if you were doing a course on the viscosity of fluids or fluid dynamics, and they said, the exam question was, describe the relationship between settling velocity and viscosity of the fluid. You think, oh, I know an equation for that, and you'd write down that equation, okay, and that would get you some marks. But if you defined all of the terms in that equation, if you said mu is viscosity, rho is density, g is traditionally the acceleration due to gravity on Earth, yes, which is not a constant, but we'll just let that fly. And r in this case is the radius of your particle. Okay. So if we were asked to rearrange that equation, okay, to do some experiments perhaps with some different size particles or different density particles to work out the viscosity of the fluid, okay, we'd want to do some maths on that, right? Okay, and we think, well, in this case it would be very simple to rearrange that equation to get, did it be mu equals something? Does anybody feel confident about, or does anybody... So I can't get you to type that into the top hat thing because you'd be doing ages trying to get all the Greek symbols. So in this case, all we would do is we times both sides by mu, okay? And that would be, let's just do it. Let's just do it, be fun. So settling velocity equals 2/9. Yeah, I can totally remember what it is. 2/9. The density difference, so I'm just going to put big delta rho. So the difference in density between the particle and the fluid. Doesn't matter that I've put it in there. I'll just do it. Density of the particle minus the density of the fluid divided by mu times gr squared. Okay? Now, if I times both sides by mu, so I times by mu and times by mu, okay? This side has got mu divided by mu. Okay, so that's just equal to 1, something divided by itself. How many u's are there in u? There's only one u in u, right? So that cancels out, giving us this equation. And then if I then divide both sides by the settling velocity, okay, settling velocity divided by itself is 1, so that disappears. Okay, 1 mu equals mu. Okay, so I've done some maths. I think I've got my equation now. How do I know that I've done that right? Okay, one of the things I can do is I can go through, okay, and just check that my units make sense. Okay, now because I know a bit about viscosity, I know that the units of viscosity are in Pascal seconds. Yeah. Okay. Now, what I then need to do is look at what's on this side of the equation, okay, and look at the units of all of these things and figure out if that also is in Pascal seconds. Okay. Now, so the first thing I need to do is figure out what Pascal seconds are, right? Because that is not an SI unit. Okay. Does anybody know what a Pascal is? So Pascal is actually a unit of pressure. So it's force per unit area. So do you know what the unit of force is? Anybody?
The Newton.
Yeah. So we've got newtons per metre squared. So I put a -2 there. So that's the same as writing newtons. Newtons over metres squared. Okay. That's the same. Yeah. So all I've done is call it metres to the -2, right? Remember from last time that if you have a negative exponent, that just means divided by that thing raised to that power. Okay, so I've got newtons per metre squared. Seconds. Is newtons a standard unit? No. No, it's not. So a newton is the amount of force required to accelerate 1 kilogram by 1 metres per second. Yeah? So that's the acceleration there, so it would be kilograms per meters per meters per second. I think meters. That's right. Kilogram. I did have this on my phone. Sorry, I did write it out on a piece of paper and then forgot it. Which is kind of like saying the dog ate my homework. I know it's really weak. There you go. See, the internet is useful. Yeah, so it's kilograms, meters per second. Meters per second squared. So that's the same as writing meters. Okay? So that's what 1 newton is. Okay? But now times by a metre squared times by a second. So that's what the units of viscosity are. Okay? And then you can look at that and think, well, that cancels, doesn't it? So cancel that and one of those, and we'll cancel that and one of those. So actually we're looking to make kilograms per metre per second. Okay? Now if we then look at this side of the equation, over here, so density. So what are the units of density? It's kind of weight per volume, right? Sorry, or mass per volume. Okay? The units of density are kilograms per metre, so kilograms per metre cubed. Okay? So where you've got density minus a density, what are the units of the answer of that little part of the equation going to be in? If you do density minus density, your answer is going to be in density. Yeah? So in this case, we don't have to worry about what happens to the units when we're minusing one thing from another. Okay? Also, if you are going to minus one thing from another in an equation, they have to be in the same units. Okay? You can't take 4 kilograms minus 5 meters. That just makes absolutely no sense on a whole bunch of different levels, right? So we've got that, 2 divided by 9. What are the units of 2 divided by 9? Trick question, there are no units to 2 divided by 9. Okay, so we can ignore that. Velocity squared. Sorry, velocity. What are the units of velocity?
Meters per second.
Yeah, meters per second. Or 80 miles per hour, right, from the other side of it. That's a douchebag, right? So meters per second. Okay? Gravity. What units is gravity in? I did give a bit of a clue early on. The acceleration due to gravity. It could be newtons. It's in. It would only be newtons if you had a mass, right? Okay. So newtons is a force. Gravitation is an acceleration. Okay. So gravity is actually. Okay. So gravity itself, like the force of gravity, is big G. Okay, and that's the force due to an object having lots of mass. Okay. The result of that is an acceleration, right? So things are accelerated towards the thing with mass. So the pen is accelerated down. Okay? So accelerations are in meters, meters per second squared. Yep. And R, the radius of our pebble, our volcanic bomb, our plankton falling through the ocean. So it's a length.
Meters.
So the unit of that is meters, okay? But in this case, the equation says it's meters squared. Yeah? So what we would then do is we'd then compare this side of the equation, which is kilograms, meters minus 1, seconds minus 1. Then we'd see if this whole fiasco over this side, okay, is that the same as that? Okay, so we can have a look at that and say, well, let's cancel out some of the easy stuff. That meters cancels that meters, okay? Seconds to the minus 1 and a second to minus 2 here, so we can cancel that out. That becomes to the minus 1. Okay? Now we've got kilograms, and there's no other kilograms at all, right? So it's going to be kilograms. We've got meters cubed, okay? Meters to the minus 3 times meters to the minus 2. Okay? That's going to become meters to the... If you're timesing exponents together, what do you do? You add. So what's minus 3 plus 2?
Minus 1.
And seconds, we've only just got 1 second on the top now. If you count it this way, seconds to the minus 1. Okay? These are now the same. Okay? They were always the same. Okay? But now by rearranging and checking all of those units, we're now pretty confident in that first rearranging that we've done, and that was a very simple rearranging. You will have to do much more complex rearranging throughout your lives, I guess. So you can use this tool of checking that the units are right, okay, just to see if the equations have been rearranged correctly. And actually, I was reviewing a paper a couple of months ago where some scientists had been kind of basically rearranging simple equations to come up with some measure about how long water stays underneath the ice in Greenland from when it melts at the surface, goes along the base of this glacier. And they've used all kinds of clever geochemistry using radioactive isotopes, and they've rearranged their equation wrong. And it was very easy to spot for me, because I just looked at the equation, I thought, you're timesing something per second by atoms, okay? And your answer is in years. I was like, no, that you can't do that, okay? You could maybe turn the seconds into years, but you can't turn an equation that has numbers of atoms into years. And that caused their paper to be rejected, and smugness for me. Okay, so this is the kind of general advice I'm trying to get across here. So when you're doing these kind of tutorial exercises, get the number of significant figures right, all these kind of things that kind of, easy way to lose marks. Yeah? If you've asked to draw a graph, you've not labelled the axes. I mean, how easy is it to label the axes on a graph? Okay? You should always do that kind of thing. And this goes for other courses as well. I mean, some other lecturers might be a little more crazy and lenient, but you get loads of marks for doing this kind of stuff. Really easy. So when you're working with equations, if you convert all of the information you're given into SI units, okay, so if you make up an equation and it's got lots of, we'll just go through an example. If you convert everything into, for instance, here you might have speeds in kilometers an hour and meters per second, okay? And if you were to include those two things in your equation, you'd get the wrong answer because you're using the wrong units, right? So, if, for instance, here we have density in grams per centimetre cubed and density in pounds per kind of cubic inch or something, yeah? Then if we just divide minus one number from the other, we just get the wrong answer, okay? So it's a good idea to convert all of the variables you're going to plug into your equation into the same units before you start manipulating the equation. Now, if you end up having really stupidly large or stupidly small numbers, that doesn't matter, because if you use scientific notation, okay, you just have lots of 10s to the power of 9, 10 to the power of 3. You just have lots of those things in your equation, which are easy to deal with. Okay, so yeah, let's just go through this example, because this is also how we might use a thing that we call guesstimation, okay, to kind of help us work out answers, right? So when they were originally figuring out how long to make a meter, okay, well, when they were figuring out how long to make a number of different units, initially quite a lot of the standard lengths and weights and measures that were chosen were actually quite arbitrary. Didn't make let's make a foot about that long, right? Or the length of somebody's arm, or the emperor's foot, or something ridiculous. But when I think in the 18th century, just before the French Revolution, the kind of royal astronomer to France or something came up with the idea of having a standard length of a meter that was actually based on something physical about the Earth. And what basically he said, it was almost certainly a he, that works, is take the Earth in green, okay, and this is kind of the equator running around it, yep, and arbitrarily that's kind of Paris with the Eiffel Tower, so they took a line from the North Pole to the equator, okay, that went through Paris, okay, they said, well, we're going to measure how long that is, and they did measure how long that was, and they're going to say 1 metre is 1/10,000,000th of that distance, okay? So I've given you that piece of information, okay, and I've also given you a piece of information that is how much the Earth weighs, 5.9 something zetatons, okay, which is a bizarre unit, but it's tons times 10 to the 21. Okay, so we'll just go through this example, and I've given you these weird bits of information, okay, because this is one of the hardest parts of this maths course. Okay, so the actual techniques of maths and rearranging equations and doing quadratic expansions and doing calculus and statistics and things like that, that's quite hard. I find that quite difficult. But the hardest part is figuring out from a question like this, okay, and figuring out like the question we had like the last time with the speed and distance and time, what maths we have to do from that information, okay? So what I'm asking you to do is to work out what the density of the Earth is in grams per centimetre cubed, okay? So one thing we could do, well, first of all, what things do we need to know to work out the density? Got the mass. What else do we need? Volume. Yeah, exactly. And have I given you the volume? No, because I'm evil and nasty. So what we do have is this piece of information here. Okay? So does anybody know what the equation for the volume of the Earth is? I'll use big R. Q. So equations that have volume in, to work out the volume of something, almost always, in fact always do, have length times itself 3 times. Okay? And to get the volume of a sphere, okay, I've assumed that the Earth is a sphere, which it isn't, but 4/3 pi r h. Okay? So do we have r? Do we know what the radius of the Earth is? Is it up here somewhere? You can work it out from the circumference, yeah? So this is part of the evil and hard part of the question, is working out what maths to do from that equation. Okay, so yeah, so actually, this distance here, okay, is actually if we move that, put Paris here now, that's Paris, is that distance there, right? You get 1, 2, 3, 4 of those distances, okay? So the circumference of the Earth is 40 million metres. Everyone happy with that? Okay, so what we can do is we can say, we can make an equation that the circumference, we can just call that C, yeah, equals 4.0. And actually, because we know this, that's an absolute number. We know that because the definition of a metre is that it's that, right? 4.00000000. Yeah, times 10 to the 7. Yeah, that is the same as 40 million. Yeah, and that is equal to 2 pi r. Yeah, the circumference of a circle is 2 pi r. Okay, so we could rearrange that equation to work out r. 2 pi. Okay, and then we could put that into this equation up here. Okay, so we could make an equation that the volume equals 4.0. You could put out all of the zeros if you want to do, times 10 to the 7 divided by 2 pi all cubed. Okay, times pi times 4 over 3. Okay. So that gives us the volume. Okay, and in this case, we could then, to get the density, so rho Earth is equal to mass, that's big M for mass, divided by volume, which would be equal to, what that is, 5.9 something something, 5.9 something something something, 7, 2, it doesn't really matter what it is, 5.97, okay, times 10 to the 21 divided by V. I'm not going to type all that stuff there. Okay, and we can then just plug those numbers in and we get the answer. Okay, would that answer be correct? No, it would not be correct because I want the answer in grams per centimetre cubed. Okay, and it's once you've started doing all of these kind of like crazy calculations here, if you then want to convert it into grams per centimetre cubed, it's a little bit more complex than just how many centimetres are in a metre. Okay, because it's metres cubed, so how many cubic centimetres are there in a cubic metre? So it's actually 100 times 100 times 100, which is kind of like 100,000. Yeah? No, 10,000. Some number, right? 10 to the 3. No. 10 to the 2 times 3, so it's 10 to the 6. Yeah, a million. There's 100 centimetres in a metre times 100 times 100, which is the same as 100 cubed, which is the same as 10 to the 2 times 3, which would be 10 to the 6. A million! Here we go. That was tedious. So what is best to do, rather than do that and get confused, like I did, deliberately, is to, before you start plugging numbers into this equation here, okay, convert them all, so convert your mass of the Earth into grams, okay? Convert your radius of the Earth into centimetres, okay? And you'll get crazy kind of like, you start to have very, very large exponents, yeah? The number of grams here, so how many kilograms are there in a tonne? 1,000. How many grams are there in a kilogram? 1,000. So to do that, we can do that very easily. So our number would be 5.97219 times 10 to the 21 times 10 to the 3 times 10 to the 3, or just times 10 to the 6. And we can do that in our heads because we just need to add 6 to 21. So to convert that into grams, it's just that number times 10 to the 26. Okay? Then you put it into this equation over here, and then you'll get the right number. Okay? Now, so that's just a, and I'll tell you what, so this is a, I'll see if I can set this for a homework. Oh, this will be exciting if this works.